Good afternoon, everyone. So today we'll be starting the new unit, that's the work, energy, and power. So we discussed about the Newton's laws of motion, right? We discussed about the force. Now we will discuss about the work done, right? Work done by the force. So first of all, we'll be discussing the work and then energy, and then at last we'll discuss the power, right? So in physics, you know that a work is said to be done when a force applied to a body or an object displaces it through a small displacement as right. Whenever an external force displaces a body, and we say that work has been done, right? You can see here in this picture, like if this is an object, right? If this is an object and we apply a force on this object, force F at an angle of theta with respect to the horizontal, and this force F displaces this object by a displacement S, right? Then we say that work has been done, right? Work has been done. So the work is done only when a force applied to an object displaces it, right? Even if when the force is applied to an object, but it does not displace it, right? But it does not displace it, right? Then we said that work done is zero, right? Let's suppose there is a huge ball here, right? Huge stone, right? Huge stone on the surface, right? Huge stone on the surface. And we try to apply force on this stone, right? We apply a force on this stone, we try to displace this stone, but the displacement of this stone is actually zero, right? This stone does not displace at all, right? The displacement for this stone is zero, right? Displacement for this stone is zero. Then we say that the work done is also zero because this force does not produce any displacement to this stone, right? So the work is only done when an external force applied on an object uh, displaces a object through small displacement or whatever displacement. Work is said to be done, right? So here this is the force F, right? Now let's suppose at an angle of theta, force F is applied, right? Force F is applied on an object, and this force displaces this object by displacement S. Then the work done by this constant force is given by dot product of this force vector with this displacement vector, right? It's given by F dot S. So work done mathematically is defined as the dot product of force and displacement, right? Or we can write it as F dot S, F as cos of theta, F as cos of theta. So it means that work done by a constant force is the dot product of constant force vector and the displacement vector. That will give us the net work done by this force, right? So you can see here it actually for work done is a theta dependent, right? It depends upon the angle between the displacement vector and the force vector, right? So for different angles, for this different displacements, the work done will be different, right? The SI unit of work is nothing. SI unit of work is Newton meter, right? Newton meter, or we call it as joule, right? Or joule. And let's suppose 1 Newton of force displaces a body by displacement of 1 meter, right? Then the work done is nothing, right? Work done is nothing. It will be equal to if the force is along the direction of displacement, then work done is 1 joule, right? Provided theta is equal to 0 degree, right? Theta is equal to 0 degree, correct? Then we say that work done is actually equal to 1 joule, right? So it means that we can clearly see that for different angles with respect to the displacement, force can produce can do different amount of work, right? So we can see what are the possibilities of work, right? We know that work is a F dot S is a scalar product, right? It's a scalar product, right? So doing a scalar product of two vectors, we get the scalar quantity, right? Which means that work is a scalar quantity. Work is a scalar quantity. Work is a scalar quantity, right? So this is SI unit of work is joule, right? And the CGS unit is equal to erg, right? and 1 joule is equal to 10 to the power 7 ergs, right? So this is the relation between 1 joule and CGS unit, right? Now talking about different types of work, the work can be positive, it can be zero, it can be negative as well, right? Depending upon the orientation of force vector and the displacement vector, right? Depending upon the angle between the force vector and the displacement vector, right? You can see here, if the angle between the force vector and the displacement vector is less than 90 degree, or we can say theta is acute, right? Theta is acute. Then in that case, the work done will be positive because work done can be written as W is equal to Fs cos of theta, right? Fs cos of theta, right? So for theta less than 90 degree, for theta less than 90 degree, right? Or greater than 0 degree, right? Or greater than 0 degree, uh, the value of cos theta will be a positive, right? Cos theta is positive, right? It is positive, correct? Therefore, work done will be a positive work done, right? Positive work done. Or we can say W will be greater than 0, right? So if the angle between the force and the displacement is less than 90 degrees, then the work done will be positive, right? Similarly, work done can be 0 if the displacement, if the body is displaced by along this surface, right, by a displacement of S, right, by a displacement of S, but the only force acting on this body is F, that's perpendicular to the direction of this displacement, then in that case work done will be F as cos of theta, right? And the angle between force and the displacement here is 90 degrees, so it will be F as cos of 90 degree, and we know cos 90 is 0, right? So the work done here in this case will be 0. So whenever displacement is normal to the external force or perpendicular to the external force, then the work done has to be equal to 0, right? In that case, work done will be nothing, it will be 0. Whenever force vector is normal or perpendicular to the displacement vector, right? Then the work done in that case will be equal to 0. So it will be a 0 work, right? So positive work is possible when angle between the force vector and the displacement vector is acute, that's less than 90 degree. And if angle between the force and displacement vector is 90 degree, then the work done is equal to 0, right? Similarly, we can have a concept of negative work, right? The negative work is done, right? Let's suppose theta is greater than 90 degree, right? Greater than 90 degree. It's a greater than 90 degree, or we can say the angle between the force vector and the displacement vector is obtuse angle, right? If the angle between the force vector and the displacement vector is an obtuse angle, right? Then in that case, the work done by the force will be negative, right? We can write this work done is equal to Fs cos of theta, Fs cos of theta, right? Fs cos of theta. So angle between the force vector and the displacement vector here is greater than 90 degree, right? It's acute angle. You can see here it's acute angle. So when theta is greater than 90, theta is greater than 90 degree, then cos of theta will have the negative values. That's less than 0, right? It will have negative values, right? So if cos of theta has the negative value, then work done has to be a negative, right? Or we can say work done will be less than 0, right? Less than 0, correct? So work done is negative when the angle between the force vector and displacement vector is greater than 90 degree, right? The work done is said to be a negative work done, right? Now let's try to calculate the work done by this constant force, right? You can see here if displacement of a particle is given by S vector, that's I cap plus 4j cap plus k cap, right? Meter due to a force 2I cap plus 3j cap plus k cap Newton. Then find work done by this force. We have to find the work done by this force. So work done by this force is nothing. It's given as work done is nothing. It's equal to F vector dot with S vector, right? F vector dot with S vector. This is the work done, right? So F vector is given as 2I cap plus 3j cap plus 4k cap, right? 4k cap. It's dotted with I cap plus 4j cap plus k cap, right? So its dot product will be 2 multiplied by 1, right? And 3 multiplied by 4 and the 4 multiplied by 1, right? So it will be 2 plus 12 plus 4, right? It will be equal to 17 joules. So the amount of work done in displacing this body from by this displacement given in this question, the work done is 17 joules, right? Let's move on to the next question. The question says a force F 4I cap minus 3J cap minus 7K cap Newton displaces a particle from a position 0, 1, 4 to point B 2, 3, 2, right? Then find the work done by this force. It means that it means that let's suppose we have this Cartesian system, right? Cartesian system. This is y explain, right? Y explain. And in this Cartesian system, initially we had an object at position. Let's suppose at position, object was at position A, right? Object was at position A. So this was the initial position vector for this object, and the coordinate of this position vector was 0, 1, comma 4, right? 0, 1, comma 4. Now what happens is that this particle displaces like this, right? Now it has some final position P, and the coordinate of this final position is given as 2 comma 3 comma 2, right? 2 comma 3 comma 2. So it will have a final position vector, right? This is the final position vector. Let me call this as Ri, that's the initial position vector, and let me call this as Rf, this is the final position vector, right? Now the particle has displaced, right, from initial position to final position vector, right? So the displacement vector here will be nothing, it will be the final position vector minus the initial position vector, right? Minus initial position vector, right? The initial position vector in the vector form is Ri, that's equal to Ri vector, that's 0, that will be 0 I cap, right? Plus j cap plus 4k cap, right? And similarly, final position vector here will be equal to 2 I cap plus 3 j cap plus 2k cap, right? So the displacement vector will be S vector, that will be R final minus R initial, that is 2 I cap plus 3 j cap plus 2k cap minus j cap minus 4k cap, right? So it will be S vector will be equal to 2 I cap plus 2 j cap minus 2k cap. So this is the displacement vector, right? If this is the displacement vector and the force vector is given as F vector, that's given as 4 I cap minus 3 j cap minus 7k cap. So this is the force vector. Therefore, the work done by this force will be F dot S. It will be F dot S. So F dot S is nothing. It's 4 I cap minus 3 j cap minus 7k cap dot producted with this displacement vector, right? Minus 2k cap, right? So we'll do the dot product. 4 into 2 will be 8. Minus 3 into 2 will be minus 6. And minus 7 into minus 2 will be plus 14, right? Plus 14, right? So it will be equal to 16, right? 16 joules. So 16 joules of work is done in displacing the body from position 0, 1, 4 to the position 2, 3, 2, right? So this is the amount of work done, right? Now let's try to calculate the work done by the constant forces as well, right? So you can see here a body of mass 20 kg is at rest, a force of 5 Newton is applied on it. Calculate the work done in the first second, right? We have to calculate the work done in the first second, right? So we can solve it, right? First of all, we'll calculate the displacement, right? Displacement by this constant force. It means that let's suppose we have placed a body of mass 20 kg here and we're applying a force of 5 Newton on this body. The mass of this body is 20 kg, right? 20 kg is the mass of this body. And after 1 second, it will have some displacement, right? And let's suppose S is the displacement for this body, right? And for the time t equal to 1 second, after time t equal to 1 second, so we have to calculate the displacement, right? Displacement. So initially this body was at rest, so initial velocity was 0, right? So this body has a constant force, so it must have constant acceleration, that will be equal to 5 net force, right? That will be equal to net force on this body, that's F upon net mass of this body, that will be 5 upon 20, right? 5 upon 20, but that will be equal to 1 upon 4 meter per second square. This is the acceleration of this body. So therefore, the displacement of this body will be S is equal to ut plus half at square. So u is 0. It will be half at square, right? Half at square. So we have to calculate the displacement after 1 second, first second. So t equal to 1, right? For t equal to 1, t equal to 1, we have the value of S equal to half a. A is 1 upon 4. T square, that will be 1 square, right? 1 square. So it will be 1 upon 8, right? Therefore, the work done will be force multiplied by the displacement, right? Force multiplied by the displacement. So force here is 5 newtons and the displacement here is 1 upon 8. So work done by this force will be 5 upon 8 joules, right? 5 upon 8 joules. So this will be the work done by this force of 5 newton on this body, right? Now discuss let's discuss about the work done by variable force, right? Work done by the variable forces. Now let's suppose if the force is not a constant, it's a variable force, right? So let's suppose on this curve here, you can see on this curve here, a body is moving from position A to position B along this path, right? Along this path, the body is moving from position A to position B, right? And the force is a variable force, right? Angle between force and displacement vector can is also variable, right? It's a variable angle, right? Now let's suppose for a very small displacement, let's suppose there is a small displacement, right? Small displacement ds vector, right? This is the small displacement vector ds vector, and for this small displacement vector ds, right? For ds vector at this instant, the angle between force and displacement vector is theta, right? Force and displacement vector is theta. So for this small displacement ds vector, there will be work done by this force, that is tw, right? So work done will be tw, right? So F is the force. So angle between ds vector, it's a small displacement, and force vector is equal to theta, is theta, right? Is theta. Now let's suppose for this for small displacement, the work done is tw, right? Work done is tw. So this work done will be nothing. It will be the force vector dotted with this small displacement vector ds vector, right? Ds vector. And we know that every vector has three components, right? So this ds vector will also have three components, right? It can have component along x, component along y, component along z. So we can write this ds vector as dx I cap, right? It's the x component, the dy j cap. This is the y component, right? This is the dz k cap. That's the z component of this ds vector, right? So it has three components, one component along x, one component along y, another component along z. So this ds vector has three components, right? Now dw is equal to f dot ds. So the total work done will be given by the integration, integrating the both sides will get the total work done. So integral of dw will be w. That will be equal to integral of f dot ds, right? F dot ds, right? Right. So we also have force can have three components, right? If can have it can have a component along x, that's fx I cap, that's fy j cap plus fz k cap, right? We can write a force like this also, right? Now let's substitute the vector equations of these forces. So it will be integral of fx I cap plus fy j cap, right? Plus fz k cap, right? Fz k cap dotted with displacement vector, that's dxi cap plus dy j cap, right? Plus dz k cap. So this work, total work done by this variable force will be nothing. It will be integral of fx dotted with dx. It will be integral of fx dx, right? Plus integral of fy dy, right? Plus integral of fz dz. So this will be the total work done. This will be the total work done by this variable force, right? So this will be the general equation for the calculation of the work done by a force. So this is the general equation to calculate the work done by a force. Whether the force is a constant or a variable, we can use this equation to calculate the work done by the constant force as well as the work done by the variable force, right? F dot S equation for of the work done is only applicable for the constant forces, right? Constant forces. But if we have variable force, we have to go by the integration, right? By this equation, we can use this We can use this equation for both constant forces as well as variable forces, right? Now let's try to solve few questions, right? Or with respect to it. Now, first of all, we'll just discuss about the different types of work done, right? We know that work done equation was fx dx plus fy dy, right? Fy dy plus fz dz, right? Now let's for some time say that the particle moves along x only, right? If the particle moves along x only, then in that case, its y will be constant or dy will be equal to 0, right? Its z will also be a constant, or we can say tz will be equal to 0, right? So in that case, work done will be only across, it will be along only x direction. That's fx dx, right? So this will be the work done in that case when particle is only moving along the x direction or along the x-axis, and y coordinate of this particle is constant. Z coordinate is also constant. So dy will be 0, dz will also be equal to 0, right? Now you can see that if we integrate it with the limits x1 to x2, this will give us the total work done, right, between the two position x1 and x2 for this particle, right? And this is a definite integral, right? And we know definite integrals represent the area under the curve, right? It's a definite integral, right? And they represent area under the curve, right? Area under force and displacement, right? Force and displacement. So the area, if this is the force vector along y and along x where the displacement, right? So if we plot between the force and displacement, if this is the curve between the force and displacement, then the area under this curve, this whole area will give us the work done by this force, right? This will give us the work done. If we calculate the area of this curve, area under this curve, total area, right? Between positions x1 to x2, this will give us the work done in displacing a body from position x1 to position x2, right? So this area will be nothing. This area will be nothing. It will be area will be equal to work done, right? This area will be equal to work done. So this area will be equal to work done. So the area under force and displacement graph gives us the work done, right, between the two positions, right? Now let's see work done by the spring force, right? Work done by the spring force. We know that whenever we extend a uh, we have a spring block system. Whenever a spring is extended by a small force, right, is extended by a small displacement, right, with the help of external force, right? For a displacement x, the spring force developed in the spring is given by the minus kx, right, where x is the extension in the spring and k is the spring constant or stiffness constant, and it is always opposite to the direction of the extension, right? If we compress the spring, the force will be in the opposite direction. The same way for the extension, the force will also be in the opposite direction. So this is the force developed in case of springs, right? Now let's suppose let's suppose if this is the extension, the force will be in the opposite direction, right? Force will be opposite direction. That will be equal to minus kx, or we can say that in this spring, this will be the direction of force. That will be equal to minus kx. So this much of force will be developed. Now, if we displace a block by a displacement Tx, then in that case, the force will be applied by this spring force, right? By this spring, right? That is equal to minus Kx, right? And this spring force will do some work because there is a force acting on this block and there is a displacement of Tx, right? Displacement of dx. So the work done by this spring force will be nothing, and we know that this force is a variable force. It's not a constant force. If this is the variable force, we can calculate the work done by the spring force between the two positions x1 and x2, or x initial and x final, using the integration, that's integral of fx dx. And the only horizontal force is the spring force here, right? So we can write integral of minus kx dx, right? Minus kx dx between the positions x1, x initial to x final, right? X initial and x final. So the work done here will be minus k, integral of x square will be x square upon 2, right? X square upon 2 with the limits x initial to x final, right? With the limits x initial to x final. So it will be equal to half k x initial square minus x final square, right? So this will be the amount of work done. This will be the amount of work done, right? This will be the amount of work done in displacing a body from position x1 to x2, right, by the spring force, right? So this is nothing. This is the work done by the spring force. This is work done by spring force. So this is nothing. This is the work done by spring force. The work done by spring force is nothing. Half k xi square minus x final square. Or let's suppose if uh, initial uh, initial if initial position is 0, or we can say if initial position is taken as the origin, right, then the work done will be minus half kx square, right? Minus half kx square. So it means that the work done in that case will be negative for the spring, because the force is always opposite to the displacement vector, right? For the spring, right? That's why the work done comes out to be negative, right? Now let's try to calculate the work done by these forces, right? Work done by these forces one by one, right? So here the force acting on this body is given by F, and this F is actually equal to 3x square, right? Plus 8x plus 4, right? This is the force acting on this body, right? Now this force is a variable force because you can see that it's a function of x, right? It's a quadratic function of x, right? And in the question we have to calculate the work done between the positions 2 meter and 3 meter, right? So between x equal to 2 and x equal to 3, we have to calculate the work done, right? So x1 is 2 meter and x2, that's the final position, that's equal to 3 meters, right? Along x direction. Since this is a variable force, right? So we'll be calculating the work done using the integration, right? So W will be equal to integral of fx dx, right? Fx dx. Fx dx. So this will be the work done, right? Between the limits 2 to 3, right? 2 to 3. This will be the total work done. So we'll integrate it between the limits 2 to 3. The equation is 3x square plus 8x plus 4 dx, right? Dx. So the integration of 3x square will be x cube, right? It will be x cube. It will be equal to x cube, right? And the integration of x will be x square upon 2, or it will be 8x square, 4x square, right? And integration of 4 with respect to x will be 4x with the limits 2 to 3. Now substituting the values of these limits, upper limit and the lower limit, it will be 3 cube plus 4 into 3 square plus 4 into 3 minus 2 cube minus 4 into 2 square minus 4 into 2, right? So this will be the total work done. So 3 cube is nothing, it's 27, right? 27 plus 3 square is 9, 9 into 4 is 36, right? Plus 12, right? Minus 8, minus 16, and minus 12, right? Minus 12. So this and this will go, right? It will be minus 24 and 27. That will be, well, we'll be left with 3 here. That will be 3 plus 36, right? So it will be equal to 39 joules, right? So 39 joules of work is done in displacing this body from x equal to x equal to 3 meters, right? In displacing this body from x is equal to 2 to x equal to 3 meters, right? This is the amount of work done, right? Now, calculating the work done by this force, that's 3xi cap plus 2yj cap minus 3k newtons, right? Between the positions 1, 2, 3, and 2, 1, 2, right? 1, 2, 3, and 2, 1, 2. This is how we have to calculate the work done, right? Now let's suppose initial we are body, right? Body whose initial position was A, right? Initial position was A with coordinates 1, 2, 3, right? And the final position is final position is R final, right? This is R initial. That's B. That's 2, 1, 2, right? This is the final position vector, right? This is the final position vector. Now we have to calculate the work done, right? We have to calculate the work done. We know that work done in general is nothing. It's integral of fx dx plus integral of fy dy, right? Plus integral of fz dz, right? This will be the total work done, right? This will be the total work done, right? Now we have variable force along x, variable force along y, and there's a constant force along z direction, right? Now we'll be calculating the work done. Work done will be the fx component of this force is actually 3x, right? We'll write it here 3x dx, right? And y component here is 2y. We'll write here 2y dy, right? And the z component of force here is a minus 3, right? We can write here minus 3 dz, right? Minus 3 dz. Minus 3 dz. Now we have to put the limits to this question, right? Put the limits. Now the initial x direction, x components varies from 1 to 2, and the y component varies from 2 to 1, and z component varies from 3 to 2. So it will be 1 to 2. For this limit will be 1 to 2, right? And for y, the limit will be 2 to 1. And for z, the limit will be from 3 to 2, right? 3 to 2. So this will be the limits, right? These will be the limits. So work done, total work done will be 3x square upon 2, right? X square upon 2, right? With the limits 1 to 2, right? So similarly here, it will be y square upon 2, will be left with y square only with the limits 2 to 1, right? And we will have minus 3z with the limits 3 to 2, right? 3 to 2. Substituting the upper limit and lower limit will be left with 3 upon 2, right? 2 square, that will be 4 minus 1, right? And it will be 1 minus 4, right? 1 minus 4. And here will be left with minus 3, 2 minus 3, right? 2 minus 3. So it will be equal to 9 upon 2, right? 9 upon 2 minus 3, right? So it will be plus 3, right? Plus 3. So this and this will get cancelled. Will be having the net work done of 9 by 2 joules, or we can say the net work done is 4.5 joules. So the net work done by this variable force 3x I cap plus 2h I cap and minus 3 from position A to B is 9 by 2 joules, right? So this is how we can calculate the work done by the variable forces, right? This is how we can calculate the work done by the variable forces. Now let's try to discuss the work done by this force, right? Where we have been given a force between displacement graph, right? So question says that a graph showing below is plotted between force F acting on a block kept on a horizontal floor versus position of the particle, right? Find work done on the particle when block reaches x is equal to 10 meter, right? From x equal to 0. It means from x equal to 0 to x equal to 10, we have to calculate the work done, right? And we know that the work done is nothing. Work done is nothing. Work done is the area under force and displacement graph, right? Force and displacement graph. Work done is nothing. It's the area under force and displacement graph. So in order to calculate the work done by this force, we have to calculate the area under this curve, right? Area under this curve. If we calculate the area under this curve, we'll get the total work done by this force, right? We'll get the total work done by this force. Now, how we can calculate the area under this curve? You can see we have two trapeziums here. This is the first trapezium, right? And this is the second trapezium, right? If we calculate the area of this trapezium and this trapezium as well, right, we'll get the total work done, right? And this trapezium has a positive area, right? And this trapezium has a negative area, right? Right, negative area. So we'll calculate both these areas. For trapezium 1, right, total work done is equal to area of trapezium 1 plus area of trapezium 2, right? Or we can say this is nothing, area under the curve, right? Area under the curve. area under the force displacement curve, right? So this is the work done. So for first trapezium, the area is nothing. It will be half of sum of parallel sides. And you can see parallel sides here is 6. This side is 6, right? This side is 6. And this side is from here to here, right? It's 2. That's 4 minus 2. That's 2. So sum of parallel sides will be 6 plus 2, right? 6 plus 2 and multiplied by the distance between them. The altitude here is the displacement between them, that's equal to 20. We'll multiply here with 20, right? And then we have a negative area. We'll write here negative sign, right? Now once again we have the trapezium here, right? This is the trapezium, right? The parallel sides are this side and this side is the parallel side. So this side is actually 10 minus 6, that is 4, right? And this side we have 10 minus 8, that's 2, right? So it will be half of sum of parallel sides, 4 plus 2 multiplied by the distance between them. And you can see once again the distance between them is 20, right? We multiplied here with the 20, right? The total work done will be equal to half into 8 into 20, right? Minus half into 6 to 20, right? So it will be 4 and 3. So 4 into 20 minus 3 into 20 will be left with 20 only, right? So 20 joules will be the total work done, right? Between for the displacement x equal to 0 to the x equal to 10 meter, right? So this is how we can calculate the work done by a force using the area under the curve, right? Using the area under the curve. So this will be the total work done, right? This will be the total work done and displacing a body from x equal to 0 to x equal to 10, right? Now the next concept is the energy, right? We're done with the work, right? Work has been done, right? The concept of work is over. We'll discuss now energy, right? Energy is nothing. It's actually the capacity to do the work, right? When we say that a body has energy, it means that it has the capacity or ability to do work, right? So energy is nothing, is the capacity of doing work or the ability of doing work, right? So we have different forms of the energy. We have electrical energy, we have mechanical energy, we have sound energies in our nature, right? In our surroundings, right? So, but in this chapter, we'll be mainly focusing on the mechanical energy, right? We'll not be dealing with any other part of the energy in this unit. We will not be dealing with the sound energy and the electrical energy and all. I will be dealing only with the mechanical energy, right? So we have many types of energies, right? So we can have electrical energy, right? Electrical energy. We have mechanical energy, right? And we have also what we call as sound energies and all, right? These are different forms of energies, right? Different forms of energy. But we'll be interested in mechanical energy only, right? We'll be interested in mechanical energy. So mechanical energy is nothing. It's broadly divided into two types, right? One is the kinetic energy, right? One is the kinetic energy, right? Kinetic energy. Another we have the potential energy, right? Potential energy. Potential energy. So both kinetic energy and potential energy together we call them as mechanical energy, right? Together we call them as mechanical energy, right? So let's discuss a bit about the kinetic energy, right? So kinetic energy is nothing, it's the energy. Kinetic energy is nothing, it's the energy by virtue of motion of a body. Energy by virtue of motion of a body, right? By virtue of motion of a body, right? By virtue of motion of a body. So because of whenever a body is in motion, it's moving, it has got at least one form of energy, that's the kinetic energy because of its motion, right? Let's suppose that if a body of mass m, if a body of mass m, right? If a body of mass m, if a body of mass m is moving with a speed v, right? Then the kinetic energy associated with it is given by half mv square, right? It's given by half mv square. So this is the kinetic energy associated with it. We know all forms of energy are the scalar quantities, right? They're the scalar quantities. So every energy is a scalar quantity. So energy is a scalar, right? It's a scalar. Energy is a scalar, right? Scalar having the same unit as the work done, because we know energy is the capacity of doing work. So it has the same unit as the work done. So energy is scalar having unit joules, right? So joule is the unit of energy as well, right? So we have written the kinetic energy as if the body is moving with speed v at this instant, the kinetic energy of this body is half mv square, right? Or we can write this kinetic energy if we multiplied this equation and divide this equation by m in the numerator and denominator as well, we'll get this equal to half, that's 1 upon 2m into m square into v square, right? Or we can write it as m into v whole square upon 2m, right? So you can see that we can write the kinetic energy as equal to p square upon 2m, right? P square upon 2m, right? This is the kinetic energy, right? This is the kinetic energy. This is the kinetic energy in terms of momentum, right? In terms of momentum. So where p is the momentum of a body, right? P is the momentum. P is nothing, it's the momentum of a body, right? P is the momentum of a body, right? So m is the constant. So momentum can change, kinetic energy can change. So if we differentiate kinetic energy with respect to the momentum, right, that's dk over dp, we'll get 2p over, right, 2p over 2m, right, 2p over 2m, right? So 2 and 2 will get cancelled. We'll be left with p over m, right? P over m. It means that the rate of change of kinetic energy with respect to momentum gives us p over m, right? It gives us p over m. Or we can say momentum is nothing. It can be written as m dk over dp, right? M dk over dp. So this equation sometimes is used to calculate the momentum as well, right? To calculate the momentum as well, right? Instantaneous moment. So kinetic energy is nothing, is the energy possessed by a body by virtue of its motion, right? And it is equal to half mv square. It's a scalar quantity, right? So it's independent of the position. It only depends upon the speed, right? So it is reference independent energy, right? So kinetic energy only depends upon the speed, whatever the instantaneous speed is of an object. Then half m times v square of that speed, right? Uh, gets the kinetic energy, total kinetic energy, right? In the next lecture, we'll be discussing about other forms of energy, potential energy, and then we'll be also discussing the conservation of energy and the conservation of mechanical energy, right? That will be done in the next lecture. So we'll stop here today, right? So we'll meet in the next lecture. Till then, take care and goodbye.